Welcome to lecture number 17. We are going to continue from last lecture, and on this subject of equilibrium carrier densities, this would be the last lecture. After that, we will move on to other topics. So, where were we? Let us see. So, what we had done in the previous lecture was that now we are at a point where if we plot 1 versus t versus log of carrier concentration, carrier concentration on this axis, then we had that if this is the intrinsic carrier concentration, something like this, then I am using just not necessarily same color code in this lecture, but all I am saying is that, and this is the amount of doping. For example, if it is n doped material, then this quantity is Nd minus Na. On this scale, if it is already a log scale, then you will directly read Nd minus Na, otherwise you will read log of this number. Then we had said that our behavior of the actual concentration which we get is something like this. Meaning thereby that beyond this temperature, on this side of this temperature, our material is going to be intrinsic, shown by blue line, and then on this side material will be what we call as extrinsic, or another name is that it is called exhaustion region. Owing its name, this exhaustion, owing to the fact that what has happened is that if we have EC, EV and some dopant level, then all the carriers which were at this level have also gone to the conduction band, and hence no more carriers can be there cannot be any more carriers, and hence the number of carriers has become saturated. It is in this region that we use these semiconductors. In this region, which is by which I mean this exhaustion region, it is this region, this exhaustion region, we use our semiconductors. And I ended up by mentioning that suppose you have a p-n junction, a semiconductor in which this junction, one side is p semiconductor, other side is n semiconductor. What does that mean? That means that if you keep increasing the temperature, then we know that from this curve here that behavior of semiconductor is going to become intrinsic. If this is silicon and this is also silicon, in that case what will happen? While at these temperature regions in the exhaustion region, this behaves like this region behaves like a p type semiconductor, this region behaves like a n type semiconductor. But if you keep heating it up and temperature goes really high, beyond this temperature, that means you are into this region now, then this semiconductor is also going to behave like intrinsic, and this semiconductor is also going to behave like intrinsic, meaning thereby that since both are silicon, then this junction property will be lost. It will behave as if it is one big piece of silicon all over, and hence this device will stop functioning. Ultimately, these electronic devices function because that there are junctions of p and n or something like that. So you lose the junction if you go to high temperature, and hence intrinsic region is not interesting region where we can operate the semiconductor. The region where we can operate is then exhaustion. Fine, this is where we were last time. Now what we are going to do is, today's lecture will be what I am going to show you in green portion. I am going to show to you that if you continue to reduce the temperature, that means you continue to move on this axis, then the question we want to answer is what will happen to n when temperature continues to become lower and lower. I will show it to you that carrier concentrations again begin to decrease, and what is this characteristic of this behavior I will point out to you. But before I do that, let me continue on this thought of exhaustion and intrinsic carrier concentration alone. Still let me continue on that little bit more before I go to the freeze at still lower temperatures. Let me plot this 1 by t one more time. 1 divided by t, I am plotting on this axis, and this is log of carrier concentration, maybe log of n if you wish, if we are going to log of n, in which we have this, let us say this straight line, something like this. This is the intrinsic carrier concentration. That means on this n is equal to p is equal to ni. This is the intrinsic carrier concentration, and the slope gives me the slope gives me minus E g, let me call it 1 for right now, k t. That is what the, sorry, not t, by 2 k, or I drop the minus sign, it is obvious that it is anyway negative slope. So, let me just write E g 1 by 2 k is the slope. What I mean is, suppose you have two semiconductors, one has a band gap of E g 1, other E g 2, and let us say band gap of another semiconductor is, second semiconductor is greater than that of the first semiconductor. Then what will be the intrinsic behavior? Recall that Ni went as square root of Nc Nv e to power minus Eg by 2k, 2 kBt. That is what Ni was. Clearly, then if you increase the band gap, then the carrier density will decrease. Further, this slope will become greater and greater. I am avoiding minus sign, I am simply saying more negative slope is what it will become then. Therefore, if I plot also simultaneously plot the semiconductor for Eg2 intrinsic carrier concentration, then I should plot it something like this. If the green line continues like this, then this line should be plotted like this, meaning thereby that at any temperature, this, since Eg2 is greater than Eg1, the carrier concentration will be lower, and notice the slope the way I have drawn is also steeper. This slope of course then will be minus, will be Eg2 by kBt. Will this slope be then in that case? Okay. If so, now let us do this. If now we say that I have a semiconductor which simultaneously has been doped by, let us say we have a semiconductor which has been doped by some net doping of Nd minus Na. That means is prominently more N doped than more N doped than P doped. That means more donors than acceptors. So, net doping as we have seen in semiconductor is Nd minus Na, and under these conditions the carrier concentration N, the majority carrier concentration, P of course will be much smaller, which will be Ni square then by Nd minus Na. There will be a smaller number, and we have given the example on that. So, if we look at this N, which is independent of temperature in the exhaustion region, then that would look like a line something like this. I am again plotting that exhaustion region. Here is my Nd minus Na, of course, Nd minus Na. Remember, whatever I am doing, you could plot this as log of, instead of plotting log of N, you could plot log of P if P is the majority carrier, and then you will write Na minus Nd. It is the same thing. So, whatever I am doing for donors, you could do it for acceptors, that does not change anything. All right. If so, now notice what happens. So, if I look at this behavior, then what do I see? I see that this semiconductor Eg1, which has a band gap of Eg1, for example, let us say this is silicon, and let us say this is gallium arsenide, which has a band gap 1.5 and silicon 1.1, then what will happen? That beyond this temperature, this semiconductor at this temperature semiconductor will start behaving. If you increase beyond this temperature right here, 1 by T value is more than, is less than this, then, and therefore T is more than whatever corresponds to that point. In that case, the semiconductor will start behaving like intrinsic semiconductor that we have talked about. If your Eg2, if you take a semiconductor which has a higher band gap, then that semiconductor would be able to behave like an intrinsic semiconductor to a higher temperature. Of course, have smaller value of intrinsic carrier concentration. Therefore, it takes them a greater temperature to reach same value as Nd minus Na, whatever is in your system, and hence they can operate in exhaustion region for at up to a higher temperature. Sometimes in design considerations you may have to include this as well. So, that is the another point I wanted to make to you, let you know about, want to tell you about before I move on to what is called as carrier freeze out. What we are saying is this, that when temperature was high, the dominant mechanism, in fact dominant mechanism was the carriers which came because of this region. the carriers came because of and corresponding holes here, because these electrons jumped over. Because these electrons jumped over across the band gap, therefore, we got intrinsic semiconductor, and we plotted out this curve right here like this. Now, when the temperature became lower, when the temperature was lowered, that means we are moving in this direction. What happened was, at some point of time, this the carrier concentration here was determined by the dopant level. We have ED as the dopant level, and then now what happened was, these carriers became, the jumps which became possible were these jumps. Well, not these jumps became possible, they were always possible when this jump was happening, this green one. At that time, obviously this is smaller energy gap, and hence these jumps were happening anyways. These jumps were anyways smaller jumps across the dopant level happening anyways, just that the carrier concentration, because of these intrinsic jumps, was so high that this number, because of this, was much smaller. But now, as you lower the temperature, the intrinsic carrier concentration, the one because of these jumps, qualitatively at least, becomes small, and this particular number, because of this, which was happening earlier also, becomes the more dominant one, and in that case what happens is, my curve starts taking a shape of like this. Okay. Now, you will also recall that I had given an example where I had said that if you have a situation like this, EC, EV, and then let us say I have certain donor levels like this, and I have some acceptor levels like this, and I had said that suppose there are NA of these, and suppose there are ND of these, and I had said that, well, this is ED level, and this is EA level, this is EA level. Then I had said that if you were to look at a picture at 0k, if you look at 0k, then what happens? My electrons are tied, the electrons are tied up to these levels. Just wait a minute, and I am going to erase some of these. And then I had said that at 0k, what will happen? These electrons, some of these electrons will go down here and reach here, even at 0k, because they will, that way they will lower their energy. So, I am going to remove these electrons from here, these 4 electrons. I remove these 4 electrons, but then I am showing you at 0k, these 3 electrons at least here still bound to their, these electrons right here, here and here, these 3 in this picture is still bound to their phosphorus atom. For example, if phosphorus is a donor in silicon, in that case these 3 electrons are still bound to the phosphorus, as 5th electron is still bound to the phosphorus atom at 0k. Clearly, that means in this case we know that the carrier concentration would be very low, because nothing is there in the conduction band. So, we clearly know that if we continue to go down in lower temperature, then this carrier concentration must somehow come down, must begin to come down. That we know. What the nature is, whether straight line, how it will come down, that we have to discuss, but that is what is called as carrier freeze out. This is what we mean by carrier freeze out, that even at the dopant level, now the carriers will not be able to contribute to conduction, and they slowly and slowly, some of these the 5th electrons of phosphorus in silicon, for example, will remain, temperature has become so low that there is not enough energy, thermal energy, to even extract that 5th electron out to the conduction band, and therefore, the carrier concentration will again begin to drop down. It is this statistics now we are beginning to learn about. So, that is what I am going to do right now. So, again what we will do is consider a semiconductor in which ND is greater than NA. You are free to consider a semiconductor where I take example where donors are more than acceptors. You are free to take example where acceptors are more than donors, does not matter. In that case, you must talk in terms of P, number of holes per unit volume, but because that is the majority carrier in that case. All right, if it is so, then Fermi level lies close to ED level. We have seen this, and I have gone through very carefully with you that when Fermi level is exactly at ED level, then half of the impurities are ionized. That means, remember this 5 at all in the exhaustion region, all the impurities, temperature was high enough, all the impurities were ionized, everything had gone to conduction band. But now if Fermi energy was at, say, exactly at the donor level, then what happens? Half of these donors are ionized and half of them are not ionized. That means fifth electron is still tied to the donor atom. So that's what is going to happen at low temperature. So it's close to ED level at low temperature. So what is the low temperature? Then what would happen in this case is what we will like to try to understand. And I will draw my picture again. In this case, I will again draw the same picture which I drew on the last page, EC, EV, and then I am going to draw those 6, 7 of these, again these acceptor levels. So NA is smaller than ND, so I have shown 7 lines, 7 segments here for ED level at ED level, and at EA level I am showing you only 4 because that represents NA, number of such sites per unit volume, and this is ND, number of such sites, number of phosphorus atoms or number of boron atoms in case of Na, number of phosphorus atoms in case of Nd per unit volume, of course, always. If so, then I have already drawn the picture for you that what happens is that some of these, now in this picture, that I will be ionized, some of the phosphorus atoms, not I will be ionized, but some of these atoms will be ionized and some will not be ionized. Maybe I am showing you 1 electron due to here going down here, and there is the electron here, at some low temperature these electrons has gone down here schematically. That is not necessarily exactly how it happens, and these are the ones low temperature is low enough, these have still not ionized. That is what is happening. So what do we see? Since Na is smaller than Nd, so first thing we know is since Na is smaller than Nd, then therefore all acceptors must be ionized. That is, Na should be equal to Na minus, all those which are ionized. Why? You can see that schematically I have shown you, even at 0 K, whatever is all these electrons would have fallen down to minimize the energy, and therefore Na would be completely ionized. The boron would have accepted for example, a boron in silicon would have accepted these electrons and would have become B minus. That means it is ionized, it is having 4 electrons, and clearly that will happen because Fermi energy is lying somewhere close to ED level. Fermi energy is somewhere close to ED level. If Fermi energy is close to ED level, then that also says you have your formula Na minus divided by Na, and you can see that if Fermi energy is somewhere here, we have done this exercise, that means all these Na levels will be ionized. Okay. If so, then how can I write charge neutrality? If I write charge neutrality, then I know N plus Na minus should be equal to Nd plus. That's what should that's what the condition for charge neutrality should be, and this is a condition where P is much less than N, of course. Otherwise, I should have, or I should, let me add P. Let me add in here P first, and then I am going to say that I am going to use this assumption. I will use this assumption, and that N is much greater than P, since it is N doped semiconductor. We have seen that N doped semiconductor, N product Np is Ni square. Since N is dominating, therefore, since N is dominating, so I am making assumption N is much greater than P. This is assumption I am making, and in most cases it will be true. So if that is so, then I will write this expression as N plus Na. I will replace Na minus by Na is equal to Nd plus, and I will drop this P in favor of Nd plus. Anyway, Nd plus, you can imagine, is on order of 10 to power 16 or 10 to power 17 per centimeter cube. This quantity Nd is, and therefore P will be a small number in comparison, therefore. All right. If so, now let us substitute this. What is Nd? Nd plus by Nd, you will recall, is of course e to power is equal to Ef minus Ed by kBt. it is this quantity. So, I will substitute this in here, and therefore, N plus Na should become equal to Nd times sorry, I made a mistake in this expression right here. So, first let me correct this, that is not the expression as we know it. So, that should be equal to 1 divided by 1 plus e to power that factor which I had written out, E f minus E d by k b t. So, I am going to substitute this now in there. So, that is why it is N d divided by 1 e power E f minus E d divided by k b t. All right. Now, I am going to do this little manipulation in here, N plus N a, I am going to write this as N d divided by 1 plus e to power E f minus E c by k b t, and I am going to write e to power E c minus E d by k b t is what I will write this as. Now, you will recognize what this quantity is. You will recognize what this quantity is. This E f minus E c is a factor which appears in N also. So, I will use this expression in here, that remember N is equal to N c times e to power E f minus E c by k b t. Therefore, I will use this expression in here, and therefore, I will write on next page, I will move this, I will substitute this quantity by N divided by N c is what I will substitute this as equal to, and then accordingly I will write this expression as N plus N a should be equal to, therefore, N d divided by 1 plus N c divided by N e to power, let us see what is that. So, this quantity we determine as N by N c. So, we will substitute in here, sorry, N by N c, N by N c e to power E c minus E d, E c minus E d divided by k b t. So, what we are going to do is now separate these terms in here, and I am going to so this way we have gotten rid of E f at least in this expression, and what I am going to do is write this as N plus N a plus N plus N a times N e to power E c minus E d by k b t by N c equal to N d, and hence I will write this as N plus N a times N e to power E c minus E d by k b t divided by N c as N d minus N a minus N, and therefore, I will write my final expression will be N plus N a divided by N d minus N a minus N as equal to 1 by N c e to power E d minus E c by k b t. So, I have changed the order, E d is here, E c is here. So, when I will take it down, take it inverted one inverse of that, then in that case, in fact, I should not write 1 by N c, but I should write N c times. So, I should take in there the other side. So, this is N c times, I take this on the right hand side and take this quantity on the left hand side. So, this is N c times e to power, and I have changed the minus sign here. So, this is the expression which we use our governing equation, which using which we will try to understand what the behavior in freeze out is. So, what I am going to do is, first we will take a case, 3 cases we will take. So, case 1, this is green one. Let us consider case 1. Let us take Na to be equal to 0. Thereby, that is, let us say we have doped only with donor atoms, no acceptor atoms are there, and at low T, and so that is what we are talking about, low temperatures, N is, let us assume, much less than, N is less than, that means we are trying to discuss freeze out. So, N has become, Nd is the most dominant one. Let me try to explain this to you through this curve, where is that curve gone, which I want to use. What I am saying is, since this value in that case would represent Nd minus Na, and Na is 0, then we are talking about value of N values are becoming lower and lower. We are talking about when N values are freezing out, that means carriers are freezing out. So, N is becoming less and less compared to Nd. So, that is the case we are considering, N is less than Nd. In that case, what happens? Now, we are considering case where, so let us see that Na is 0, this quantity Na is 0, N is much smaller than Nd. So, in the denominator I am going to only keep Nd therefore, and in numerator of course, Na is 0. So, I am going to leave it as N square, this will make it N square equal to Nc e to power Ed minus Ec by kBt. And what is Ec minus Ed? Remember this, here is Ed level, here is Ec level, here is Ed level. So, it is measuring this distance. It is basically minus of this separation right here. The dopant level measured from the band edge is what we are gotten into. All right. So, if that is the case, then clearly what is implies what is the value of N? N in that case is equal to, N goes as in that case Nc Nd square root e to power Ed minus Ec by Ed minus Ec by 2 kBt. That means N versus temperature, that means log of N versus 1 by T will have a slope of Ec minus Ed by 2 k. What does that mean? In intrinsic case, remember this slope was, first of all it will be straight line. First of all, you can see if I take log of N, then I will have a straight line as a function of 1 by T. Second, I will have a slope which corresponds to this gap, just like this out if you wish. So, the way I will plot it out is as follows. So, we will plot it as carrier concentrations as log of N now as something like this, and then I am going to plot a straight line like this, and this value of course will be equal to Nd, Na is 0 of course, and this slope will be equal to, Ec minus Ed by 2 k. Would this slope be, and carrier is clearly showing that begin to freeze out, the carrier concentration begin to decrease. Now, let us take case 2. This is a case where Na is not equal to 0, Na is not equal to 0. This leads to other interesting facts, some more interesting facts. Now, in this I can, for, or I should not say case 2 first, let us say if Na is not equal to 0, then I have two cases possible, namely that N is less than Na, and another case, this is case, we will call it 2 now, and in case 3, that means I will call where N is greater than Na. N is less than, and remember it's always true that Nd is the most dominant one, is greater than Na, and Nd is greater than N also. So, only matter is this is always given in case 2 and 3. Then we have question is between N and Na, which one is bigger. N is in one case, in case 2 we will consider N less than Na, in case 3 we will consider N greater than Na, and we will see the consequence of this. So, let us write down all these. Nd greater than Na, that is given, and Nd greater than N, this is understood already, and the case 2 is basically where N is less than Na, or much less than, we will make it much less than when we want to make the approximation. So, this is basically the case 2 is what it is we are indicating with. So, if this is so, then remember, let us go back to our expression N plus Na divided by Nd minus Na minus N was equal to Nc e to power Ed minus Ec divided by kBt. All right. If that is the case, now we are going to make this approximation, and we are going to say N is much smaller than Na. In that case, we will drop this N in favor of this Na, and therefore, I am going to write this as N. So, we will approximate this as N times Na. Now, numerator will become N times Na, because I am going to drop this N. This N is much smaller compared to Na, and in denominator I could just simply write Nd, because anyway Na and Nr is smaller, much smaller than Na. That we can always do, because Nd is the most dominant one. Therefore, Nc e to power Ed minus Ec kBt. Again, what do you observe? Log of n versus 1 by t is linear, and slope is E c minus Ed by kb. That is the slope now. Earlier we had a slope of 2k, remember 2k. Now what has happened? This slope has become, now this slope has become 1k. Slope has changed. All right. So, this is when n is less than Na. Before I draw this, let us start looking at also the case where when n is greater than Na, and then we will draw this case 3 also, and then we will draw all these together. So, now let us look at case 3, in which case n we are going to take as greater than Na, all other things remain same, namely Nd is greater than. So, in other words, in this case the order is n greater than Na. In the previous case, of course, the order of things was, therefore, the order of things was Nd was Na was greater than N, N was less than, that was the order of the concentrations. Now, it is Nd, N and then Na. So, if that is the case, again let us go back to our expression N plus Na divided by Nd minus Na minus N equal to Nc e to power Ed minus Ec by kBt. If so, then we can again make the substitution in here, that this time N is greater than Na. Therefore, I am going to drop Na in favor of N. So, I am going to write this numerator as N square again, and of course, denominator as Nd, because Nd anyway is greater than either of these two. So, I am going to write this as Nc e to power Ed minus Ec by kBt. Now, notice I have N square. So, again if I plot log of N versus 1 by t. Again, what do we notice? It's linear. Second, slope is now again two kb again. This is n square. When I take a square root, I will get a 2 here, factor of 2 here. So, again becomes 2 kb. That is very interesting. That means the slope changes in between. So, now we are in a position to plot this whole curve. So, I have already plotted the case where Na was equal to 0 and you saw the slope was this, whatever this gap, energy gap was, meaning thereby that it is EC and here was ED, then whatever this gap, energy gap was, that gap is written here, EC minus ED, that is written here. The point is more important, this factor 2. There is a factor 2, that was the slope of this line which we had when Na was equal to 0. What happens at the end? Now I am going to plot what happens when Na is not equal to 0. In that case, I will get two cases. One, so log of n, or not log, natural log, since I am plotting, since I am writing slope as all right. Now, what will happen? Now, we have two cases where when, let us see, right, let us repeat it down. When n is less than Na, then slope is 1 k here, not 2, 1 is appearing here, when n is less than Na. So, when n is less than Na, then our slope is becoming, then the slope is, in that case, slope is EC minus ED by KB, and a minus sign here, of course. And when n is, this was case 2 and case 3 was n greater than Na. In that case, you can see that when n is greater than Na, we got a slope which had a factor of 2 in there. So, we will write this as minus EC minus ED by 2 kb. So, when n is greater than, so slope will become half in magnitude. Slope will become half when n is greater than Na, and it will become more when slope become more when n is less than Na. So, the way I will draw this is something like this, and then something like this. At some point here it is changing. The slope here is, in this case, this is, let us give a name because this is becoming very big. So, if this is EC, if this is ED, if this is ED and this is EV, then let us give this as a name. This difference, this magnitude to be equal to, let us call it as, let us give it a name, let us give it a ED prime, where ED prime is equal to EC minus ED. That is what this quantity is. That is what this quantity is. So, I am going to plot this as the slope here is when n is greater than Na, then I am going to write this as ED prime by 2 kb, and the slope here is minus ED prime by kb. And what is this point? This point right here, let me use a different pen here, well, it is right here where the slopes break, that point should be equal to, on this scale, should be equal to Na, right. You understand this? So, if I label and this entire curve, then I will write it this as follows. This quantity, the slope would be Eg by 2k. If you wish, I can put a minus sign here. You understand that it is a minus in there. I was normally not writing it. And then what is it? This point represents a concentration which is equal to Nd minus Na. This represents Nd minus Na. Now, up to this point, we have region. This is a region case 2 where case 3, sorry, this is case 3 here, which are n is greater than Na. So, now the n which I am plotting here, log n is what I am plotting in this axis, on this axis, that number is falling down, And by the way, keep remembering, because I am assuming that we are plotting this on a semi-log type of graph paper. So, the numbers we read out here is NA, on a number we read out here is ND minus NA, but otherwise if you log value taken, then you can think of this as a log. I should write log in front of it also if you wish, depends on how you want to read it. Anyways, so with that I hope you understand that part. So, if I look at case 3, then n was equal to ND minus NA, and ND of course was very large. Let us say this is 10 to the power 17, this number is 10 to the power 17 or something like that, and this number is equal to 10 to the power, let us say 15. So, then n starts becoming less than ND, of course, that means becomes less than 10 to the power 17, but it continues to be greater than NA. Let us say it is in order of 10 to the power 16, that means it is more than this quantity NA here. Then in that case our slope is ED prime by 2k, but as you can see, when n becomes less than NA, that means goes below 10 to the power 15, less than 10 to the power 15, in that case the slope changes. So, the point where the slope changes is roughly where n is equal to NA, and hence I have used this point to mark as this value as being that means this value must be equal to NA. That is what I am assuming, that is what I have pointed out to you, and then the slope here, all right. So, using this, this is now you can see first physically let us see the whole picture. The whole picture looks like this, that I have a system in which I have some electrons which are bound to this level. We are at very low temperature, and there are some acceptor levels also. Let us say acceptors levels few there are some acceptor levels also which have these have taken their electrons, they are ionized, and I have only this is a picture at 0k, this is picture at 0k, and we can add here plus also in here. This is the picture at 0k, and what has happened is as we begin to raise temperature, then we start getting some electrons jumping from here to here, and that is what we see in this region here. That is what we are seeing in case 2, and this is the case 2. In case 2 and 3 are these regions where some n, I have shown here 2, some of them have started jumping over to this because temperature is slightly increased, and hence this jumps are becoming possible. As this temperature continues to increase, the point comes when all of these electrons have jumped. When all of these electrons jump, and that is basically the start of this point we are reaching here. Now, as we keep increasing the temperature, these jumps are still not possible, the temperature is low enough, and hence we get into a situation where semiconductor is where carrier concentration remains same, which is, and this quantity is obviously equal to ND minus NA. This is equal to ND minus NA. So, we find that carrier concentration remains the same as you continue to increase temperature, and that is ND minus NA is where it remains to until temperature becomes high enough that these electron jumps also become possible, and then the behavior becomes intrinsic like behavior. That is the big picture of this semiconductor. But also please notice that this is a very powerful way, this is a powerful experiment. Why I have taught you is it is a good characterization technique. What you notice? Suppose you measured carrier concentration in a full temperature range from very low to reasonably high temperature. What are the different information can you get? What are the different information you can get out of it? Notice this is essentially ED prime. You can ED prime, and this quantity is EG, this quantity is EG. If you see from this, you are able to extract just by doing this experiment, measuring carrier concentration as a function of temperature, whole temperature range, things which you can get is you can measure ED. That means, if you measure this and calculate these slopes, then you will measure this ED. You will be able to measure these ED levels. Second thing you will be able to see is that where are the slope breaks. When you see a break in slope, in that case you see you can measure what NA value is, you can figure out how many of these NA are present in there, what is the number of these acceptor levels present in there. When you see a flat region, you can measure out what is ND minus NA, you can measure out what is ND minus NA, and hence you can figure out what this total number of ND levels are, how many ND are present in there. And finally, when you go higher in temperatures, you can also measure the band gap of the semiconductor. So, in one experiment you can measure the band gap of semiconductor, you can measure the dopant level with respect to the measure this dopant level with respect to the relevant band edge, that means EC minus ED, that gap you can measure, and you are able to do so because there are thermally activated jumps, and there are two types of thermally activated jumps happening, one across this gap and other across this gap, and that is why you are able to measure both these gaps. So, ED prime, this ED prime you should be able to measure, you should be able to measure the band gap, you should be able to measure ND minus NA, and you should be able to measure NA. This much information you are able to get out of this one experiment. Only one which you are not able to measure figure out is what is this energy level, and this of course you are not able to measure because no transition is, no jumps of electrons are taking place between these valence band and the dopant level, acceptor level are taking place. So, how could you measure them? So, that is the only one. So, hence it is this carrier freeze out experiment is a very powerful technique to be able to measure all these quantities. Of course, you would ask the question, how would you measure N? Measuring N is not a trivial exercise. You could measure N using a Hall probe experiment, Hall measurement you can do to measure N. Alternative is that you can measure, instead of N, you could measure possibly conductivity. You could measure possibly conductivity, and since conductivity is equal to N times number of carriers times mobility times the charge, the basic fundamental charge, and if you make an assumption that mobility is not a very strong temperature function of temperature, then more or less what you measure by sigma is what you measure in N, if you make that assumption. So, this measurement is fairly simple, a 4-point probe like measurement will give you conductivity, and accordingly you can measure N. Therefore, similarly, by the way, I have taken an example where ND was greater than NA, you could have measured, you could have a situation where NA is greater than ND, in which case then I would be plotting as a function of 1 by T, I will be plotting log of P, and it will be straightforward enough to say that these curves will look something like this, where actually now I will be measuring ND here and measuring NA minus ND here, NA minus ND, just same analysis you can do. This of course remains the same, it measures EG by 2K minus if you wish, and what I will be measuring here then in this case would be EA minus EV by 2K, and this will be KB EA minus EV by KB. So, these are the quantities we will be measuring just by same analysis. Now, in this case it will be log of P that will be plotted in this direction. So, you will be able to measure whether it is if it is a P type semiconductor, then this is how you will measure it, or if N type, then this curve is what you will measure out. All right. So, this brings us to the end of this. I hope you are able to understand this whole equilibrium carrier densities. Why this is taught is because the reason is this, I have mentioned earlier also. These are equilibrium carrier densities, and from now on our operation range will be confined between these two temperatures. So, our room temperature will choose semiconductors, only those semiconductors whose room temperature lies somewhere between these. So, room temperature should be between this range, or temperature of operation of that semiconductor must be in this range, because this is the range in which semiconductor devices will be made. This is the range in which semiconductor devices, exhaustion region or extrinsic semiconductor will be with which we will be making these devices. And now from now on I will assume that this is where we are operating in this condition. In this condition we will never go to low temperature or high temperature range as far as devices are concerned. Okay. Now, when you make devices, when you apply voltage, you are disturbing this equilibrium. So, I had said in the beginning itself, this to knowing equilibrium carrier density is important, because you want to know that when you disturb the system, then we will have to watch out how will this system like to come back to equilibrium. So, in order to see the rates of how fast it tries to come back to its equilibrium, then you must know where the equilibrium is, and hence we have described the equilibrium. From now on, we will start discussing about those processes which disturb this equilibrium, and after that we can start talking about devices. So, let me close this chapter here today with equilibrium carrier concentrations, and next time we will start with new topic on which will lead us towards devices. Thank you.